Lorenz series expansion of a function. So contents are we will discuss Lorenz series and we will discuss few problems. Okay. So first of all, recall what is Taylor series. Okay. So what is Taylor series? Taylor series expansion. That means if f of z is analytic at a point z naught. Okay, so this is our complex plane and this is the domain. So some z naught is a point here. Then if f of z is analytic at a point z naught, then f of z can be represented as Taylor series expansion. So that is f of z equal to, that means we have a series expansion n equal to 0 to infinity f nth derivative at z naught divided by n factorial z minus z naught all power n, n. Okay, so this series expansion is valid in a circle or disk. So that means if you take a disk with the radius r, that means our boundary of this disk is z minus z naught is equal to r, this circle, and radius is r. So this series expansion is valid for any point inside this circle, and it's not valid for any point outside the circle. So this is the circle where the f of z has a series expansion, and the radius of this circle is called radius of convergence. So the thing is, if you have a function is analytic at a point z naught, then there exists a circle with radius r such that if you take any point inside this f of z series expansion is valid. Okay. Now we will discuss Lorenz series expansion. So, so this is Lorenz series expansion. Now, uh, okay. So, so, so the thing is, to, okay, if we have Taylor series expansion all with the center z naught. That means we have this expansion in the form f of z naught plus f dash of z naught be divided by 1 factorial z minus z naught plus f double dash of z naught divided by 2 factorial z minus z naught all square plus etc. So this expansion in z minus z naught, right? That means center is z naught. So that means that expansion happens only when f of z is analytic at z naught. Okay. So what next? My question is: does there exist? Question is: does there exist a series expansion of f of z uh, if f of z is not analytic at z naught? That means is അവിടെ ഒരു എഫ് ഓഫ് സെറ്റിൻ്റെ ഒരു സീരീസ് എക്സ്പാൻഷൻ വിത്ത് സെൻറ്റർ z naught if f of z is not analytic at z naught, or next question, can we find a series expansion outside this circle with the same center? If you take any point here, can we make a series expansion outside the circle? So for Taylor series, we need this function must be analytic, and uh, series expansion only valid inside some circle with radius r. Okay. So now we will extend this concept to non-analytic functions or other functions. So this is very important. We will discuss that. So that's why we will discuss a Lorenz series expansion. So, so let f of z be analytic in a domain containing two concentric circles C1 and C2 with the center Z0 and the annulus between them. That means, so we have a function f of z and Z0 be a point here, and we have two circles. I will show you what is it. Okay. This circle is C2 and this circle is C1. So this is C2, C1. So we need the function must be analytic. Function must be analytic. Function must be analytic inside this annular region. So here the function should be analytic. The condition is we doesn't need analyticity at z0, but we need analyticity. That means function must be analytic uh, in this annular region. Then so for Taylor series we need analyticity at z0, but for Laurent series we need only analytic in the annular region. Then f of z can be represented by a Laurent series. So this is Laurent series. What is Laurent series? F of z is equal to sigma n equal to 0 to infinity a n z minus z naught all power n plus sigma n equal to 1 to infinity b n divided by z minus z naught all power n. So this is the series expansion. So this is equal to a naught plus a1 z minus z naught plus a2 z minus z naught all square plus etc. plus b1 z minus z naught plus b2 z minus z naught b2 divided by z minus z naught all square plus etc. So this is the Laurent series expansion of f of z, where the condition is the function must be analytic in a annular region. Then we can find a series expansion with the center z minus z naught. Okay. So now what? So for Taylor series we have sigma n equal to 0 to infinity a n z minus z naught all power n, and we know that a n is f n factorial at z naught, sorry, f nth derivative at z naught n factor. So we precisely we know what is the constant a n's, but here the thing is we have to find out this unknown an and bn. If we know an and bn, then we can find the Taylor series expansion. So if we know an n equal to 1 2 0 1 2 etc., that means a1 a2 etc., and b1 b2 etc. So these are the unknowns. If we find these unknowns, we can find the uh, Laurent series expansion. So this Laurent series expansion consisting of non-negative and negative powers, the coefficient of Laurent series. So the thing is, the coefficient of Laurent series can be find an is equal to 1 by 2 factor 1 by 2 pi I integral over c f of z divided by z minus z naught all power n plus 1 dz. Bn is equal to 1 by 2 pi integral z minus z naught all power n minus 1 f into f of z dz. where C is any simple closed curve lies in the annular region, uh, annulus, and encircles the inner circle. Okay. So, so the thing is, this is our uh, this is our is a any simple closed curve. Now, okay. So the thing is, it is very difficult to find out an by using this formula. So we will not use this formula. Okay, for finding an, we will use another tricks to find the an and bn. Okay, so don't worry about these formulas. We will find very easy techniques to we will develop easy techniques to find an and bn, or Lorenz series expansion. So now the series now the series converges, and f of z in the annular region obtained by this. Okay. Now, a special case, important special case, if Z naught is the only singular point of f of z inside C. So, this is our annular region. Okay. So, f of z is analytic. Suppose Z naught is only point inside this non-analytic region, non-analytic point, then this can be shrink into this point. So our annular region becomes this. Okay. A disk without its center. Okay, so that is the one thing. Now one more important thing is, so we call this part, that means the expansion series with the negative powers of n is called the principal part. So what is principal part? Principal part of Lorenz series is this: sigma n equal to 1 to infinity bn by z minus z naught all power n, that is b naught plus b1, sorry, that is b1 by z minus z naught, b2 by z minus z naught all square plus etc. Okay, so you get a idea about Lorenz series. So what is Lorenz series? Lorenz series expansion must be if when does this exist, does there, so why we define Lorenz series? We want a Lorenz series expansion of f of z with the center z naught if f of z is not analytic, and second is we want a series representation of f of z outside the circle of convergence. So now we will so I told you that we will not use this formula for finding an and bn, but rather we will use some techniques. So the thing is, the Lorenz series of an analytic function in its annulus of convergence is unique. So if you have a Lorenz series expansion z naught in this annular region with the center z naught, then any Lorenz series expansion of f of z must be unique. There must not have any other Lorenz series expansion. So if you find any series representation of f of z in this annular region, then that must be the Lorenz series expansion. So however, if you find another big, sorry, so but if you find any other annular region, there may be different Lorenz series expansion. അതായത് ഒരേ ആനുലാർ റീജിയൻ ആണെങ്കിൽ ലോറൻസ് സീരീസ് എക്സ്പാൻഷൻ യുണീക്ക് ആയിരിക്കും. ഇനി ഇതേ ഫംഗ്ഷൻ്റെ വേറൊരു ആനുലാർ റീജിയനിൽ എക്സ്പാൻഷൻ എടുത്തു കഴിഞ്ഞാൽ ലോറൻസ് സീരീസ് എക്സ്പാൻഷൻ മേ ബി ഡിഫറെൻറ്റ്. ഓക്കെ, So this uniqueness we will use to find it. So the thing is, we will use Taylor series to obtain the coefficient of Lorenz series. അതുകൊണ്ടാണ് ഞാൻ ടൈലർ ആൻഡ് മെക്ലോറിൻ സീരീസ് ഒരുപാട് ചെയ്തത്, 3 ക്ലാസ്സോളം ചെയ്തത്. വി വാണ്ട് ടു ഫൈൻഡ് ഔട്ട് ലോറൻസ് സീരീസ് എക്സ്പാൻഷൻ യൂസിങ് ടൈലർ സീരീസ് എക്സ്പാൻഷൻ. ഓക്കെ, so if you have any doubt you can ask me. So this is overall idea about Lorenz series. So it's very somewhat difficult, but while doing problem it becomes very easy, because if you know Taylor and Maclaurin series very well, then Lorentz series is very easy. Then after that everything up to residue integration must be very easy. Okay, so the first question is find so if you have any doubt you can ask me. Okay, so the question is find Lorentz series expansion of z raised to minus 5 sin z with the center 0. So we have f of z is given z raised to minus 5 sin z is equal to 1 by z raised to 5 sin z. Okay, now we want the expansion in 0. That means z minus 0 powers. Okay, and we know that this is not analytic at z naught 0. Okay, this function is not analytic at 0, because 0, if z equal to 0 denominator becomes 0. So this point the function is not analytic, and all other points function is analytic. So our we will take the annular region 0 less than mod z minus our center is 0 less than infinity. So there is no other points where f is not analytic. So this is our annular region. In this annular region we will find Lorentz series. Now, okay, so we know Maclaurin series expansion of sin z. What is Maclaurin series expansion of sin z? Sin z. Okay, so Maclaurin series expansion of sin z is sigma. So the thing is, you have to by heart or something, you have to know what are the expansion of basic functions like sin z, e raised to z, 1 by 1 minus z, 1 by 1 plus z, 1 by 1 minus z all square. So such basic function you have to know the series expansion. This is n equal to 0 to infinity minus 1 power n. Okay, z raised to 2n plus 1 divided by 2n plus 1 factorial. So this is z minus z cubed by 3 factorial plus z raised to 5 by 5 factorial minus etc. So this expansion of with the center 0, right? Okay. Now f of z is equal to 1 by z raised to 5 sin z. This can be written as 1 by z raised to 5. Here this center is 0, right? Z minus 0 all raised to 5 into, now we will use this expansion, z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus z raised to 7 by 7 factorial plus etc. So we will multiply this, and this you will get 1 by z raised to 4 minus 1 by z square into 3 factorial plus 1 by 5 factorial minus z square by 7 factorial plus etc. So we get and this is valid when 0 less than mod z less than infinity, right? So this is a series representation of f of z, 1 by z raised to 5 sin z on this annular region 0 less than mod z less than infinity. So this is the, thus by the uniqueness this must be the Lorenz series expansion of 1 by z raised to 5 sin z. Okay, so okay, so what is the principal part here? Principal part means you have a എന്തായിരിക്കണം ഡിനോമിനേറ്ററിൽ z മൈനസ് z നോട്ട് പവർ. അപ്പം ഇതായിരിക്കും അതിൻ്റെ പ്രിൻസിപ്പൽ പാർട്ട്, റൈറ്റ്? ഇവിടെ പ്രിൻസിപ്പൽ പാർട്ട് എന്താണ്? Part is in this expansion only this 1 by z raised to 4 minus 1 by z square 3 factorial. So ഇവിടെയാണ് ഡിനോമിനേറ്ററിൽ the power negative powers of z. Okay, and all now after that everything will be positive powers of z. Okay, so this is the Lorenz series expansion. So we will not use that formula of an and bn, rather we will use Taylor or Maclaurin series to find the Lorenz series. So next problem, if you have any doubt, you can ask me. We will discuss this deeply because it's very important. Develop 1 by 1 minus z. First one, a in non-negative powers of z and b in negative powers of z. So we want to find out the Lorenz series expansion of f of z is equal to 1 by 1 minus z. So now where this function is not analytic, f of z is not analytic at z equal to 1, right? Z equal to 1, then denominator becomes. So first we will consider the region, this region. So we have Lorenz series expansion. So this is 0, this is 1. So the point, this point, the function is not analytic. So now first I will consider this circle. It is, so in this circle the function has a series expansion, right? So that must be, this is mod z equal to 1. That means mod z less than 1. So in this circle we have a series expansion. That must be Taylor series expansion because in this circle the function is analytic, right? At every point the function is analytic in this circle. So the first in this circle the Lorenz series is same as Taylor series or Maclaurin series. So we want the expansion in z form. That means z minus 0. Center must be z naught is equal to 0. So first we will find for mod z less than 1. We have the series expansion 1 by 1 minus z is equal to 1. We know that 1 plus z square plus z cube plus etc. So this is valid when mod z less than 1. Since f of z is analytic at in mod z less than 1, the Lorenz series the Lorenz series is same as Maclaurin series of 1 by 1 minus z. Okay. So here the for when mod z less than 1, 1 by 1 minus z is equal to sigma n equal to 0 to infinity z power n. So here the positive powers of z, right? N. Z ന്റെ powers എന്താണ്? N 1, 2, 3, etc. ആണ്. Okay. So now we will consider. So this now we will consider the region outside this circle. Second part. So this is it. So now our annular region is so now for second part, for 1 less than mod z less than infinity. That means now our annular region is this region. That means outside this circle. So inside that circle we have a Taylor series expansion of Maclaurin. Now we want to find the series representation outside this circle. So what is that annular region? 1 less than mod z less than infinity. Okay. Now so what we will do is we have f of z is equal to 1 by 1 minus z. Okay. So this implies, okay, 1 less than mod z less than infinity means mod z greater than 1, right? Means, so this means set of all z such that mod z greater than 1. So if mod z greater than 1, we have 1 by mod z less than 1, right? Mod z greater than 1 ആണെങ്കിൽ, if you take reciprocal, 1 by mod z must be less than 1. Now what we will do, we will do a trick. We already know what is Maclaurin series expansion of 1 minus 1 by 1 minus z is 1 plus z square plus z cube plus etc. This valid when mod z less than. Now here our expand here for mod z greater than 1, we have 1 by mod z less than 1, and this never becomes 0 because this is outside mod z, z equal to 1, right? So what we will do is we will make it in some form like this, right? So we have 1 by 1 minus z. If I take minus z outside, then what will happen? Minus 1 by z plus 1. Okay. So this I can written as minus z 1 minus 1 by z. So this is equal to minus 1 by z into 1 by 1 minus. Now the thing is, we already know mod z less than 1, then 1 by 1 minus z has a series representation like this. Now here for mod z greater than 1, we have 1 by mod z less than 1. Okay, so this is less than 1, right? So for mod z greater than 1, or this means mod less than 1, sorry, 1 less than mod z less than infinity. So this implies 1 by mod z less than 1. So now we can represent 1 minus 1 by z is equal to minus 1 by 1 minus z. So now we will this is already less than 1. So we will use the Maclaurin series representation. So this can be written as minus z. Now we will replace z by, here z by 1 by z. Okay, so this is equal to 1 plus 1 by z plus 1 by z square plus 1 by z all cube plus etc. So this is valid when mod z 1 by mod z less than 1. So that means mod z greater than. So what is the Lorenz series expansion of 1 by 1 minus z out in 1 less than mod z less than infinity? This is equal to minus 1 by z plus, sorry, minus 1 by z square minus 1 by z cube minus 1 by z raised to 4 minus etc. So this is the Laurent series expansion outside the circle. So this is something difficult. You have to do more and more problem. So for this problem, first we find the point at which f of z is not analytic, and then we find a circle. Here there is a series representation, that is already we know, Maclaurin series or Taylor series. Then outside what we done is we will make it into ആ ഫോമിലേക്ക് കൺവേർട്ട് ചെയ്ത് ഇതാണ് മോഡ് z greater than 1 or 0 less, sorry, 1 less than mod z less than infinity 1 by 1 minus z expansion. So I will stop here. You just practice this. So here with the center there. So I will give you a hint. You can take z cube 1 minus z. Okay. So this representation you just do find all Lorenz series. So you have to find this series representation. Okay. So we need there is two singularity, 1 and 0. So you first this circle 0 less than mod z less than 1, then you find the this both series representation. Okay. So